100 million. 100 million users, potentially millions of conversations happening at once. And somehow you type a sentence, and words start appearing almost immediately. How can a system like that possibly keep up? The first thing to understand is that an AI response isn't a web page sitting on a server waiting to be downloaded. The model has to generate the answer token by token, and every new token depends on everything that came before it. And here's the bottleneck. Large language models are enormous. Their weights have to live somewhere, and during inference, the hardware has to constantly move data between memory and compute. At scale, the problem isn't simply having enough compute. It's moving enough data fast enough. Now comes one of the biggest inference optimizations, the KV cache. As the model processes your conversation, it builds intermediate attention data for the tokens it has already seen. Instead of recomputing all of that context every time a new token arrives, the system can reuse the cached information. But the cache itself consumes GPU memory. With thousands of active conversations, that memory becomes a scarce resource. When cached data can't stay resident, the system may need to rebuild it later, creating extra work exactly when traffic is already high. Now we hit another problem, memory fragmentation. If you reserve one giant contiguous block for every conversation, you're wasting space, because conversations don't all grow at the same rate. PagedAttention changes the allocation strategy. KV cache is split into smaller blocks that can be placed wherever free memory exists. Now imagine 10 users arriving at once. With static batching, they enter together, and the short responses finish early while the GPU keeps waiting for the longest one. Continuous batching changes the scheduling model. Requests can join and leave the active workload as generation progresses, keeping the GPU busy with useful work. But token generation still has a sequential bottleneck. So here's a clever trick, speculative decoding. A smaller draft model quickly guesses several upcoming tokens. The larger model then verifies those guesses in parallel. Correct guesses are accepted, wrong ones are rejected. Instead of asking the big model to generate every token from scratch, the system tries to let it verify several at once. And large models may not fit on one GPU, so inference systems distribute the model across multiple GPUs. With tensor parallelism, pieces of the computation are split across devices, which then communicate over high-speed interconnects. So what happens when you press enter? Your request enters a distributed serving system. The scheduler decides where it should run. The system may reuse cached context. The request joins an active batch. Memory is allocated efficiently. The model runs across the available hardware, and the generated tokens are streamed back to you as they're produced. And that's the real answer. There isn't one magic optimization that makes AI inference scale. It's the stack: caching, memory management, scheduling, batching, parallelism, and model-level optimizations, all working together. And this is why inference efficiency matters so much. If you can serve more tokens with the same hardware, every optimization compounds. Better cache reuse means less recomputation. Better batching means higher utilization. Better memory management means more active users per GPU. At massive scale, milliseconds become infrastructure economics. The surprising part is that serving AI at scale isn't just about building a bigger model. It's about making every byte of memory, every GPU cycle, and every millisecond count. The next time ChatGPT starts typing before you've even finished blinking, remember, behind those few words is an entire scheduling and inference system working to keep the machine from falling over.